Hey there, pilots and future aviators. Welcome. We're going to jump into something really fundamental today: atmospheric energy. We're going to break down how the atmosphere gets its heat and, more importantly, why that matters for every single flight you take. So let's kick things off with a classic pre-flight scenario. You're on the ramp, it's a nice 20 degrees Celsius outside, but you look at your flight plan, and it says up at your cruise altitude of 8,000 feet, it's going to be a pretty cold 4 degrees. So where did all that warmth go? Well, the answer is all about the physics of the air, and we're going to break it all down step by step. Okay, first things first, we absolutely have to get our definitions straight. In our everyday lives, we kind of throw the words heat and temperature around like they're the same thing. But in meteorology, they're actually two totally different concepts. And getting this right is the foundation for everything else we're going to talk about. Let's use a classic example to make this super clear. Imagine you've got a bathtub full of warm water and a tiny cup of boiling water. The question is, which one has more heat energy? Now, your gut might say the boiling water, right? It has a way higher temperature. But the bathtub actually holds way more total heat energy, and that's just because there's so much more water in it. So what is temperature, really? It's all about the average energy. Just picture all the tiny molecules in a parcel of air. Temperature is basically a measure of how fast they're all moving around, on average. In that little cup of boiling water, those molecules are just buzzing around like crazy. That's what a high temperature is. Now heat, that's a different story. Heat is the total energy of all of those moving molecules combined. It's not the average speed, it's the grand total. The bathtub has trillions and trillions more molecules than the cup. So even though they're moving slower on average, their combined energy, the heat, is way, way bigger. So that's the big takeaway, right? Temperature is average, heat is total. Okay, so we've got a handle on what heat is. The next logical question is, how does it get from one place to another? In our atmosphere, energy is always on the move, and it mainly travels in 3 different ways. If you can get a handle on these 3, you're well on your way to understanding weather. And here they are, the big 3: conduction, convection, and radiation. And trust me, you felt all 3 of these your whole life, probably without even realizing it. So let's connect each one to what it feels like in the aviation world. First up is conduction. This is just heat transfer by touch. It's super simple. Imagine you're doing your pre-flight walk-around on a hot, sunny day. The sun's been baking that aluminum wing all morning. When you put your hand on it, it's hot. That heat is transferring directly to your hand. That's conduction. This is how the ground heats up that very thin layer of air that's touching it. Now, convection, this is the big one for us pilots. This is heat moving because the air itself is moving. So the ground heats up a parcel of air. That air gets lighter and less dense, and what does it do? It rises, carrying all that heat energy upward with it. I mean, for glider pilots, this is everything. They live for those rising columns of air we call thermals. For the rest of us, it's why sunny afternoons can get a little bumpy. And finally, we have radiation. This is energy moving as a wave, and the cool thing is it doesn't need anything to travel through. It can go right through the vacuum of space, which is how the sun's energy gets to us in the first place. You know that feeling? You're sitting in the cockpit, the cabin air is still cool, but the sun is just pouring through the canopy and warming your face? That's solar radiation at work. And all of this really brings us to the big boss, the power source for everything we've been talking about, the sun. It is the engine that drives every single bit of weather on our planet. Now, there's a technical term for all that incoming solar radiation. We call it insolation. But don't let the word scare you. Just think of it as the fuel for our planet's weather engine. How much insolation an area gets is basically the biggest factor in how hot it's going to be. And this picture really says it all, doesn't it? See, down by the equator, the sun is basically directly overhead. It's like a spotlight, concentrating all that energy in a small spot. That's high insolation, and that's why it's hot. But as you move towards the poles, those same sun rays come in at a shallow angle. That same amount of energy gets spread out over a much bigger area, so it's a lot less intense. Less insolation means it's colder. Simple as that. So the sun is constantly sending all this energy our way. But what actually happens when it gets here? I mean, the Earth doesn't just keep getting hotter and hotter, right? It maintains a pretty stable balance. Let's take a look at how our planet balances its energy checkbook.
It's actually pretty wild when you break it down. Right off the bat, almost a third, 30% of the sun's energy just gets bounced right back into space by clouds and bright surfaces. Another 19% or so gets absorbed by stuff in the atmosphere itself, like dust and gases. That means only about half of it, just 51%, makes it all the way to the ground to be absorbed by the land and oceans.
And that 30% that gets reflected? It has a name, albedo. It's basically just a measure of how reflective something is. So, a surface with a high albedo, like fresh white snow, reflects almost all the sunlight that hits it and stays cool. But a surface with a low albedo, like a dark asphalt runway, soaks up that energy like a sponge and gets incredibly hot. This is a huge deal for pilots because it's what creates those thermals we were talking about. All right, so let's put all these pieces together, radiation, conduction, albedo, and bring it right down to the surface to see how this all creates the daily temperature cycle that we as pilots have to plan for every single day. This graph right here is so important. Look closely. I want you to notice two key things. First off, see that line for the ground temperature? It goes way up and way down, much more than the air temperature just above it. The ground heats and cools really fast. Second, notice that the peaks don't light up. There's a delay. The air temperature lags behind the ground. And that lag is the critical takeaway here. Think about it. The sun is at its highest point in the sky at noon, right? That's when we're getting the most intense solar radiation. But it takes time for the ground to absorb that energy and then heat the air above it through conduction. That's why the hottest part of the day, and usually the bumpiest time to fly, isn't at noon. It's typically a few hours later, around 2 or 3 in the afternoon. Okay, here's a great question to see if all this is clicking. We've all noticed this for sure. You have 2 perfectly calm nights, but the night with some low cloud cover feels a lot warmer than the crystal clear, starry night. Why is that? Well, it all comes back to that radiation we talked about. During the day, the Earth soaks up energy from the sun. Then at night, it radiates that heat back out towards space. On a clear night, that heat just escapes. Poof, it's gone. But clouds, clouds act like a giant blanket. They're great at grabbing that outgoing heat and bouncing some of it right back down, trapping it and keeping the surface much warmer. So let's